Greetings to all my tech heads out there in the KevTechify nation, and if you're new here, welcome. In this episode, we're going to look at IP services. We'll be discussing ARP vulnerabilities, ARP cache poisoning, DNS attacks, DNS tunneling, DHCP, and finally DHCP attacks. This episode is part of my series on enterprise networking, security, and automation. I'm Kevin here at KevTechify. Let's get this adventure started. ARP, Address Resolution Protocol, has a couple vulnerabilities in it. Now, hosts, they broadcast an ARP message to all the hosts on a segment. They send it out as a broadcast. They do this to determine the MAC address of a certain IP address. They send out a request and say, hey, I am looking for this IP address. That IP address then replies back and says, hey, I'm here on this port on this switch, and my MAC address is this. Then we start building MAC address tables, filling in our ARP caches with that information. A threat actor, what they can do is send an unsolicited ARP reply. So you send out an ARP request, waiting for an ARP reply come back in. But if you send out an unsolicited ARP request, an unsolicited ARP reply, one without a request, this is called a gratuitous ARP. Other hosts on the subnet will see this gratuitous ARP and then store the MAC address and IP address that you have responded with to this reply that had no request to start with. Any host on the network can be the owner or can claim to be the owner of an IP address or MAC address just by sending out this ARP reply. So a threat actor, they can poison ARP caches. They can put wrong information in there. They can even do it in such a way where it creates a man-in-the-middle attack to redirect traffic. And when you do the man-in-the-middle attack, you can not only see traffic because all the traffic is going through you, you can actually manipulate that traffic. How can a threat actor use this to their advantage? Well, they can do ARP cache poisoning. In this scenario, we have user A over here on a PC. User A is going to say and send out an ARP request and saying, hey, IP address 10.1.1.1, where are you? That ARP request is going to hit the switch, is going to get broadcast out all the ports. All the PCs are going to hear that, but then the PC that actually belongs to that 10.1.1.1 is going to say, okay, here I am. This is me, 10.1.1.1, and my MAC address is, and in this example, we're going to use 1234556. They're going to send back that ARP reply. That ARP reply is going to be heard by the switch. We add that to the switch, and then it gets forwarded on to user A, and user A then updates its ARP table, ARP cache, and it can start communicating. Our threat actor can hear that original ARP request go out. It can hear that request going out, and then it can reply back with its own information. Even though it's wrong, even though it's not their MAC address, they can send a reply. And that reply here says, hey, I am your IP address, 10.1.1.1, but my MAC address is 987.654. They send that reply back. It goes to the switch. It overwrites that legitimate one from user B. It overwrites that legitimate MAC address, and then it gets forwarded on to user A, where that also overwrites the legitimate answer. And now, anytime information needs to go to 10.1.1.1, it's going to be sent to the threat actor's MAC address on the local area network. Welcome to ARP spoofing. This is going to be an adventure. First, we have PCA down here on the left. And PC1 down here on the left wants to communicate with the web server up here in the upper right. PC1 here is on the 192.168.1.0 network. And the web server is up here on the 192.168.2.0 network. For PC1 to get all the way up to the web server, we have to make it through our local area network and through this router, which is R1. R1 is acting as the default gateway of our network, the network that PC1 is on. With an IP address of 192.168.1.254. And R1 has the MAC address ending in 9902. PC1 needs to communicate with this MAC address in order to make it to the web server and to get a response back. Quick recap on how ARP works. In order for PC1 to get to the web server, it has to go through the router, which is its default gateway. It needs to know the MAC address of its default gateway. What we can do is open up PC1 and go into the command prompt. And what we can do here is an ipconfig /all. And with that command, we can see that PC1 has the MAC address ending in B0EE. It has an IP address of 1.10. And it knows the default gateway IP address of 192.168.1.254. However, if I take a look at my ARP cache with an ARP -A, there is nothing in there, nothing in my ARP cache. It doesn't know the MAC address of router R1. So if I was to send out a message like ping 192.168.2.100, that remote web server, the first ping is going to fail because my PC is resolving the MAC address of my default gateway. And by the time that ARP resolution happens, that ICMP request times out. But that's okay. The other three were successful. And now, when I check out my ARP cache with ARP-A, I can see that my default gateway, 1.254, is known by this MAC address ending in 9902. The lab is complete. Well, maybe not. There's one last thing to try. What I'm going to do is open up the web browser. So I've closed the command prompt, open up the web browser, and put in the web IP address of our web server right here, 192.168.2.100, and I have the web page shown for our web server. Nice simple text web page, but it shows that we are able to connect to our web server and display the page. Now that threat actor comes into play. My threat actor, I'm going to open up my threat actor, go into my command prompt, and do an ipconfig /all. And my threat actor already has an IP address on my network. It has a MAC address. This could be just a normal user on your network, just with too much time. This user has a MAC address ending in 20A8 and an IP address ending in .1.20. And it also understands that the default gateway is 192.168.1.254. What if this threat actor wanted to be a man in the middle? Well, we can make that happen. I'm going to go ahead, go over to my R1, and then go into the configuration, and then go into the interface here, gig 001. That's the interface that's connected to my local area network, the blue network we're working on. I'm going to copy this MAC address, the one that ends in 9902, the MAC address right here of our default gateway. And then we're going to go back to that threat actor machine. Right here we have our threat actor machine. And then go into the configuration and then go into the fast Ethernet port on our threat actor, and we're going to change the MAC address from what it was originally to spoof the MAC address of our default gateway, which ended in 9902. We're just going to go ahead and paste that in. We copied it from R1, the configuration there of that Ethernet interface on our LAN. We just copied it, and now we'll paste it into the MAC address on our threat actor's interface. And now that our threat actor has the MAC address of our default gateway, we can now have some fun. I would send a gratuitous ARP over to R1, but I can't do that here in Packet Tracer. Let's send a constant ping instead. And how you do a constant ping is you put the -T option in here, and the -T means continually repeat that until we terminate the process. So it'll just repeat it and repeat it for as long as you let it run. It won't run 4 times and stop. It'll continue to run. And this constant ping is going to be talking with the IP address of PC1 with the source of our threat actor with our now spoofed MAC address. And the pings start. Now that the pings have started, I'm going to show you something here on PC1. I'm going to go into the command prompt here on PC1, and I'm going to look at our ARP cache. I'm going to type in ARP space -A, and this now is our new ARP cache right here. Notice we have 2 entries. We notice that we have 2 addresses, 1.20 and 1.254, but they both have the same MAC address. Let's go over to switch 1, and let's verify our MAC address table by using the command show MAC address table dynamic. And let's take a look at the MAC address here learned off of port 2. And now the MAC address off of port 2 is the MAC address of our default gateway, ending in 9902. And now when PC1, which I'm going back to right now, tries to browse the web server at 192.168.2.100, it just times out. There is no activity here. There is no activity that's happening here because PC1 is coming here to this default gateway, and instead of routing to our correct default gateway, that traffic is routed to our threat actor. And that gives us a request timeout. And if our threat actor is running something to analyze network traffic, like this network sniffer right here, let's go ahead and connect into that. I can go in and click on one of those TCP messages. I can go ahead and scroll through, read the headers. I can even read the data. And what we can see here is the source IP address was 1.10. That was PC1. And the destination was meant to go to 2.100, which was our web server. Well, how was it then switched? Instead of going to the web server, it is then switched to the threat actor. Because off of port 2 on the switch, it thinks his MAC address 9902, which is the default gateway, which is in the path to get to the web server. The spoof was successful. If I scroll down, and you can see our source and destination ports, we were targeting port 80 here. And the man-in-the-middle attack was successful. And if we had better threat actor software, we could be capturing the data and at the same time forwarding it to the web server, acting like everything is just fine, using a beautiful but unethical man-in-the-middle attack. It was my pleasure to provide you with this wonderful episode on IP services. If you like this episode and you got value out of it, and of course, depending upon what platform you're using, please click that like button, leave a 5-star rating, give me a comment. This all helps me bring you more great content. Please take a minute to subscribe to my channel. All of my socials and contact information are on my website, KevTechify.com, and you can get all these episodes in video and podcast form. DNS is that service that matches resource names to numeric addresses, taking something like www.cisco.com and matching it to an IP address. Because once again, remember, traffic routes across networks, not using a domain name, but using an IP address. So we have to translate those names into IP addresses. DNS has a format for queries, responses, and sending data. They use resource records to identify different types of DNS responses. Now, securing your DNS, that is typically overlooked. Up till a couple of years ago, most people never thought about securing your DNSs. But with recent attacks, a lot of companies, a lot of individuals, and even internet service providers are requiring you use secure DNSs. Now, DNS attacks include DNS open resolver attacks, DNS stealth attacks, DNS domain shadow attacks, and DNS tunneling attacks. An open resolver is where clients outside of the administrative domain can query a DNS server to get entries. That DNS open resolvers are vulnerable to several attacks. One would be a DNS cache poisoning attack, where these threat actors, they send spoofed, falsified resource records with information to that resolver to redirect users from legitimate sites to malicious sites. The DNS cache is poisoned, and then that information can be used to inform that DNS resolver to use malicious name server that is providing those resource records. The second one is the DNS amplification and reflection attack. This is where that threat actor uses a denial of service attack or distributed denial of service attack on a DNS open resolver to increase the volume of answers that open resolver is trying to respond to. Now, the threat actor sends these DNS messages using IP addresses of a target host. These attacks are possible because that open resolver will respond to queries from anyone asking a question. And finally, we have DNS resource utilization attacks. This is another denial of service attack that consumes the resources of those DNS open resolvers. It consumes all available resources, so that way when a legitimate request comes in, it'll time out and that legitimate request will go unanswered and the user will not be able to get a proper response. And a lot of times that resolver either needs to be rebooted or the service needs to be stopped and restarted to recover from a denial of service attack. Threat actors use a DNS stealth attack to hide their identity. First method to do a stealth DNS attack is to use fast flux. Threat actors use this technique to hide their phishing and malware delivery site behind quickly changing networks compromised of these DNS hosts. DNS IP addresses are constantly changing, typically within minutes. Botnets often employ fast flux techniques to effectively hide malicious servers from being detected. The second method is a double IP flux. Here, the threat actors use this technique to rapidly change host name to IP address mappings, and to also change the authoritative name server. This increases the difficulty in identifying the actual source of the attack. And finally, threat actors use domain generation algorithms. This technique is used in malware to randomly generate names that can be used as rendezvous points in malware to hand data off from one point to another. In a domain shadowing attack, an account has been compromised that controls DNS. One of these accounts where you can go in and add records in a DNS server has been compromised. The threat actor then uses that account to create multiple subdomains. These multiple subdomains typically point to malicious servers, and because it was done with a valid account using a valid login, there's no alarms that go off. And so they look like legitimate domains that were set up. DNS tunneling is a interesting way of sending data, sending applications, sending malware across the network, bypassing normal firewall, normal anti-malware software mechanisms. What happens here is you have a client on your network. What we do is we take the command data, that malware, and we split it into multiple encoded chunks. There's ways you can take a program, divide it into some encoded chunks. Once you have those encoded chunks, each of those chunks is placed into a lower level domain label for a DNS query. That DNS query goes from your client to the local domain server. Because that local DNS server does not have the record, it makes a request of the authoritative DNS server. Because it's normal DNS traffic, it is allowed to travel back and forth through your firewall, past your malware, past your spyware software. It's allowed to travel. And that request makes it to this authoritative DNS server. So you need to set up a domain. You need to set it up as the authoritative one, but you also need to run some malicious software on there to reconstitute all of these chunks. And this client goes through all of these chunks from that command data, sends it out as requests. And sometimes this can be a couple hundred DNS requests. It could be up to thousands or hundreds of thousands of DNS requests, all to get these data to this compromised DNS server out on the internet. Then this DNS server reassembles that. And when we reassemble it, it could be information that was smuggled out of the company. We could work this in a reverse route, where when the DNS client requests this DNS information, when we send back the response, we could put a payload in there. And that would be, once again, one of these command datas broken up into an encoded chunk. We could send that payload back into the system. The client would get that. And once again, it passes right through our firewall, because the firewall lets DNS traffic through there, comes into our client. The client reassembles all of those encoded chunks into the malware. That malware can then be executed and an attack can happen. And so using DNS, we can actually send information in a creative way. Now, to stop DNS tunneling, you as the network administrator, you have to use filtering that inspects DNS traffic. You got to pay close attention to DNS queries that are longer than average. So you need to know when DNS queries are starting to get longer, because they have all that encoded information in there. And then those that just have suspicious names. Most of the time your DNS queries will be names, cisco.com, google.com. But if you got domain names that are 3LZPQ8749, that may be suspicious, and you might need to look at what's happening there. DHCP, Dynamic Host Configuration Protocol, they're also susceptible to attacks. DHCP, the standard process, 4 steps. We start off with our discover, where the client sends out a broadcast to everybody on the network saying, hey, I'd like to request an address. Any DHCP server out there, please respond to me. The DHCP server hears that coming in and sends out an offer. That offer is unicast because they know where it came from, what MAC address it came from, because this is all done on your local area network, what MAC address it came from, so we can send unicast back and says, hi, I'm DHCP server 1, here's the address I can offer. It gives you an IP address, the subnet mask, the default gateway, and the lease time, and any other options that your DHCP servers can figure it out. That's a unicast. Then the client gets in that offer and it sends back the request. I officially request to use this. I accept this DHCP offer. Now, that's a broadcast. Why is this a broadcast here? Well, if there was more than one DHCP server on your network that responded to your original broadcast, all the other DHCP servers that sent requests out would hear that broadcast that you're requesting, you're accepting the use of the IP address from the server. Those other DHCP servers aren't going to be used. We can return those IP addresses back into the pool and we can hand them out again. So this request goes out of broadcast to the network, and then that server sends back a unicast directed message acknowledging, yep, your acceptance is acknowledged. That is the 4-step process. And if you remember, this is the DORA process. DORA. Discover, offer, request, and acknowledgement. Standard DHCP process here. The DHCP attack that is the most common is a DHCP spoofing attack, where that threat actor sets up their own DHCP server. It's a rogue DHCP server on your network. What that means is that threat actor needs to have access to your network to be able to plug into an access port on your switch, get connectivity, and then run their own DHCP server. What happens here is that client sends out a request. It's a broadcast, so all DHCP servers hear that. Here we have a DHCP server on our local area network that's ran by our threat client. That is there. You also have another corporate DHCP server. Well, this isn't on your local network. You have to have a helper address in here. So we put in our helper address. It points it here. So the broadcast goes from your client PC to the router. The router then forwards it on to the DHCP server. Then the DHCP server sends the response back to the router. The router routes it through to the client. Which one goes quicker? Because the client uses the first response. That's the DHCP offer it accepts. Does it accept the one where we have the rogue DHCP right on our local area network? Or do we accept the official corporate one that's on the corporate network, but we have to use helper addresses, go to a different network, and then wait for that response to come back? The rogue DHCP server is the one that's used. So we now have a spoofed DHCP server on our network. Once we're communicating there, we can go through and set up several different things. In that information we hand out, we could hand out the wrong default gateway. So we could hand out the wrong default gateway. Now, why do we want to hand out the wrong default gateway? Well, that's the first step in the man-in-the-middle attack. We could set ourselves up as that default gateway where we're now all traffic is going through us, and if we have the right programs, we can in real time forward it on and inspect that data. We can set up the wrong DNS server. So we could set up wrong DNS. Why would you want to do that as a threat actor? Well, instead of pointing it to the correct website, you could point it to a malicious website where you're harvesting data. You could even set up a wrong IP address. So wrong IP address you could send to that client. Why would you do that? An invalid IP address won't work on the network. So that way that client isn't able to access anything, couldn't get to their default gateway to get off of their network, couldn't see any of the other servers on their network. This would be like a denial of service attack. All different things happen when that rogue DHCP server is on your network. It was my pleasure to provide you with this wonderful episode on IP services. If you like this episode and you got value out of it, and of course, depending upon what platform you're using, please click that like button, leave a 5-star rating, give me a comment. This all helps me bring you more great content. Please take a minute to subscribe to my channel. All of my socials and contact information are on my website, KevTechify.com, and you can get all these episodes in video and podcast form. In the upper right is my playlist for my series on enterprise networking, security, and automation. In the bottom right is one of my favorite videos that I linked just for you. Thank you so much for watching this episode on my series of enterprise networking, security, and automation. Once again, I'm Kevin. This is KevTechify. I'll see you next time for another great adventure.